Right, this is our fourth lecture on acid-base chemistry. We talk a lot about acid-base chemistry this quarter. And in this lecture, it'll be a relatively short lecture. We'll discuss the leveling effect and the Lewis definition at the end of the lecture. Okay. And the title slide kind of details the Lewis definition. And the Lewis definition is based on electron sharing. So a Lewis base is something that donates an electron pair, and a Lewis acid is something that accepts a electron pair. And in this definition, you make an acid-base complex. So this material is coming from sections 7, 8, and 9 in the book. All right, the first thing we're going to discuss is something we've sort of alluded to in previous lectures. But when you have salts that are made up of parts from weak acids, weak bases, or strong acids and strong bases, there's a way to tell if they're going to make acidic solutions or basic solutions, right? And if you have a solution that's made of salts that are from strong acids and strong bases, such as the cation of a strong base. Remember, the anion of a strong base is OH minus. So we're talking about the other parts, not the H plus or the OH minus, but the cation of the strong base and the anion of the strong acid. That mixture will be a neutral solution. And the example here is sodium nitrate. Right? Sodium, Na plus, is the cation from a strong base, right? NaOH is a strong base. The nitrate ion, NO3 minus, is the anion of a strong acid, nitric acid, HNO3. Okay, so when those solutions mix, you'll just get sodium ions and nitrate ions, and neither will really react with water to any great extent, right? They're from a strong, sodium, we wouldn't expect that to really, but in particular nitrate, when you put that into solution, right, it's not like an anion from a weak acid that we mentioned before that can take a proton from water, right? It's an anion from a strong acid, so it's going to be fully dissociated in water. So it doesn't really react with water to any great extent that would cause the solution to be acidic or basic. Okay. So how do we get a salt solution that yields acidic solutions? So an example here would be NH4Cl, ammonium chloride. Okay. A cation here in this salt, ammonium, is the cation of a weak base, or you can think of it as the conjugate acid of a weak base. Okay. And the anion is from a strong acid. So this, when in solution, you have the cation of a weak base, which is a conjugate acid, and the anion from a strong acid, which is neutral, doesn't react in water. You get an acidic solution. Right? Ammonium, again, cation of a weak base is how the book describes this, but you can think of it as the conjugate acid of that weak base. Weak acids and weak bases have conjugate pairs to them, right? And those conjugate pairs, where they're in solution by themselves, will act like, an acid or a base. Okay. Chlorine here, that's the anion of a strong acid, HCl. Okay. Chlorine isn't going to react with water at all. It's a strong electrolyte, fully dissociated. What is going to react is this ammonium, NH4+. Okay, and it reacts with water, as we've seen before, as a weak acid would, to produce NH3 and H3O+. So it raises the H3O+ concentration in the solution, thus it's acidic. Right, a salt that consists of small, highly charged metal cations and the anion from a strong acid will also yield acidic solution. So iron nitrate is a small, highly charged metal cation, iron 3. Okay. NO3 minus, remember we saw that example before, that's the anion of HNO3, nitric acid. It's not going to do anything in solution, spectator ion, but the iron will do something. Okay? The iron can react with water. If you remember, we mentioned this before, a small, highly charged cation can pull electron density away from the water protons, and one of those can actually lose a proton to the bulk water in solution, and thus it makes it the H3O plus concentration go up and it's acidic. Okay, what about salts that yield basic solutions? Well, if you do the opposite of what we talked about with an acidic solution, if you have the anion of a weak acid, which is its conjugate base, and the cation of a strong base, you'll get a basic solution. So the example here is sodium acetate. So acetate is the anion of acetic acid. Okay, acetic acid is a weak acid. So this is the anion, we call it the anion of the weak acid, or you can call it the conjugate base. Right, and sodium is just that strong cation from a strong base, NaOH, so it is a spectator ion. Right? So when the acetate ion is in solution by itself without any of the acetic acid to start, it's going to act like a base. Okay? And the solution will be basic. So the acetate ion can pull a proton from water and raise that OH minus concentration. So it will be basic. So let's try a practice question with some examples of these. Okay, so the first one, well, we have to predict whether aqueous solutions of the following are going to be acidic, basic, or neutral, and write an equation for the reaction of any ion with water. Okay, so the first one, potassium perchlorate. Well, potassium is the cation of a strong base. If you did potassium hydroxide, that'd be a strong base. Typically, those metal cations, if they have a +1 or maybe even a +2 charge, will fall in this category. Okay, so they'll be neutral. We don't have to consider them. Perchlorate, if you remember, is the anion of a strong acid, perchloric acid. Okay, so that doesn't do anything either. So this will be neutral. Right. Sodium benzoate. Right, so now we have sodium, which is just the cation from a strong base, sodium hydroxide. Can ignore that. And we're left with benzoate, C6H5COO minus. Right, so that's an anion or a conjugate base of a weak acid. So it's going to act like a base in water. It's going to pull a proton off and raise the OH minus concentration. So this will look like a base. So this solution here will be basic. Okay. And remember, this is an equilibrium, and this doesn't happen to a great extent, but it happens enough to raise that OH minus concentration to make the solution change from neutral to basic. Finally, chromium-3 nitrate. Well, nitrate is just the anion of HNO3, a strong acid, so we don't really need to consider that one. Chromium-3, however, is going to be a small, highly charged metal. In solution, what happens is you have the chromium complex with H2O in a octahedral complex. Remember that positive charge can pull some of that electron density away from a proton on water, and a bulk water molecule can steal one of the protons. So you would get chromium H2O 5 OH, so it lost one proton, and it now has this complex has a +2 charge instead of +3, and then you get H3O plus. So this in solution acts like an acid, so the solution will be acidic. Okay. Well, what happens if you have salts from weak acidic cations and weak basic anions? Well, then you're really up a creek, right? You can't really tell just by looking. We're going to have to compare the strengths of the two. Okay, so if you have a salt that consists of a cation from a weak base, right, a cation from a weak base, so it's conjugate acid, and the anion of a weak acid, which would be a conjugate base, right, the pH of the solution is going to depend on the relative strength of the acid and the base of the ions. So an example of this would be ammonium cyanate. You have ammonium, which is the conjugate acid of the weak base NH3, and you have cyanate, which is the conjugate base of a weak acid, hydrogen cyanide. So these will both react in water, right? The NH4 ammonium will give up a proton to water and make an acidic solution. The cyanate will take a proton from water and make a basic solution. So it's going to depend on, how strong each of these are, who will outweigh the other one, right? And remember, how we determine the strength of an acid or a base is by those equilibrium constants, the Ka and the Kb. So the reaction is going to proceed further to the right, whichever reaction here proceeds further to the right, as those are written, is going to determine the pH of the solution. So we need to compare the Ka for NH4 plus, because it's acting like an acid, and the Kb of Cn minus, because it's acting like a base. Okay, so we look at that. To get the Ka of NH4 plus, you might not be given that necessarily, because that's a conjugate acid from another weak base. So if you look those values up or on an exam, you might be given the Kb of NH3, right? But you don't really need that. You need the Ka of NH4 plus. Well, remember that relationship between Kw and Ka and Kb. So Ka multiplied by Kb equals Kw. So we can solve for the Ka if we're given the Kb of its conjugate base. Okay, so Kw divided by the Kb of NH3, we get 5.7 times 10 to the minus 10. And we can do the Kb for cyanate the same way. We convert using the Ka of HCN, the weak acid, Kw divided by that, and we get 1.6 times 10 to the minus 5. So in this case, the larger the Ka or Kb, the stronger it is. So we have Kb is bigger for Cn minus, so it is a stronger base than NH4 plus is an acid. So this solution will be basic, because this reaction will proceed further to the right. There'll be more OH minus than H3O plus, the top reaction. Here's a summary table of the sort of conditions we've just talked about with salts. Okay, the conditions where you get neutral salts, those are cation and anions from strong bases. The type of conditions that will give you acidic solution, the cation or conjugate acid of a weak base with an anion of a strong acid, or a small, highly charged metal cation with the anion of a strong acid. And a basic solution, we have the cation of a strong base and the anion or conjugate base of a weak acid. So cations and anions from strong acids and bases don't factor into it. We only care about the conjugate acid or base from our weak base or acids. And then solutions that could be either are going to have, basically you have the cation from a weak base, or you can have a small highly charged metal cation as well, and then an anion of a weak base. So those are the conjugate acids and bases reacting together. And for that, you really need to know the Ka to Kb ratio. Okay, so predict the relative acidity of salt solution from Ka and Kb of the ions. So let's try a problem with this. Okay. So we need to determine whether the solutions of the following salts are acidic, basic, or neutral at pH, at a temperature of 25. Okay, that really doesn't factor in to our equation here. So if we look at the first one, zinc formate. Well, zinc is a small metal cation. So that can produce, can act sort of like a acid in solution, remember. It's coordinated by water, and a bulk water molecule can pull a proton off of one of the coordinating waters to raise the H3O plus concentration. And that would be 1 plus for that complex, since we've lost a proton. And this is H3O plus. Okay, so acidic. Well, the formate now, the HCOO minus, will act like a base, right? It's the conjugate base of formic acid, which is a weak acid. So it's the anion of a weak acid. And how it reacts, it is given by this equation, right, where it can pull a proton off of water to form formic acid, and then you have OH minus, right? So it's acting like a base. Okay, so how do we address this? Well, you need the Ka value for zinc 2 plus, H2O 6. And you can look that up, right? These are in Appendix C in the book. On an exam, they will be given at the end of the exam or in the problem. So this Ka value is 1 times 10 to the minus 9th. And then you need the Kb of the formate ion. And that value you might not be able to find, but you could find the Ka for COOH, formic acid. And to convert, right, you just do the Kw divided by Ka of the acid, the weak acid. So Ka is always 1 times 10 to the minus 14. This Kw is always 1 times 10 to the minus 14. Ka is 1.8 times 10 to the minus 4. Right? You just look that value up for formic acid, and you get 5.6 times 10 to the minus 11. So how do we compare these? Well, we have a 1 times 10 to the minus 9th is bigger than 5.6 times 10 to the minus 11th. So our Ka is bigger than Kb. Right? So that means this solution, therefore, this solution will be acidic. Okay. Now let's look at the second option, change my pen color. So the second option, right, we have potassium, which is the cation of a strong base. So that doesn't do anything, doesn't factor in. We have HSO3 minus. That is the anion of a weak acid, H2SO3. Right, so this is the anion of a weak acid, or you can consider it the conjugate base of a weak acid. So this solution, this is going to act like a base in solution. Right, so what do we have here? We have HSO3 plus H2O, HSO3 minus plus H2O. HSO3 is actually kind of difficult because there's two options. It can lose a proton and act like a base, or act like an acid, or it can give up a proton, or it can grab a proton from water and act like a base. Okay, so for this one, we're going to have to compare the Ka and the Kb for our HSO3. So we can look this up, the value for Ka. Whoops. Okay, we can look this up, Ka for HSO3 minus. Right, so this is HSO3 minus. Ka value is 6.5 times 10 to the minus 8. Right, we can also look up a Ka for H2SO4. H2SO3. So its Ka value is going to be 1.4 times 10 to the minus 2. Well, that really doesn't help us, right? What we really want is the Kb of HSO3 minus. For HSO3 minus. And so that'll just be Kw divided by the Ka of H2SO3. Right? That's how we calculate the Kb of something that we can't look up because it's not in the table. Okay, so that's 1 times 10 to the minus, 1 times 10 to the 14th, negative 14th, divided by 1.4 times 10 to the minus 2. That's the value we could look up. So our Kb here is 7.1 times 10 to the minus 13th. All right, and we can see that the Ka here is bigger than the Kb, so this will also be acidic. Okay, so hopefully that looks like chicken scratch, but hopefully going through that, paying attention to that, you can see that you can compare Ka and Kb values. And if you're not given a particular Ka or Kb, remember that you can look for that conjugate acid or base for that species and convert it using the relationship between Kw. Okay. That brings us to the leveling effect. Okay. The leveling effect is something that's noticed when you put a strong acid or a strong base, for that matter, in water. Okay. All strong acids and bases are equally strong in water, and you know, that's where they get that term leveling effect, because water levels all strong acids and strong bases. Right? All strong acids will completely dissociate to form H3O+, and all strong bases completely dissociate to form OH-. So in water, the strongest acid possible is H3O+, and the strongest base possible is OH-. Right, so let's explain that. What does that mean? Well, I got this slide from another source because I think it does a better explanation than our book. Right, because water can act as an acid or a base, it's going to have this leveling effect on strong acids and strong bases. So say we have a very strong acid, right? H2SO4, sulfuric acid. Well, none of that H2SO4 is going to be around in water, because water is going to take away those protons. It's going to dissociate completely. So the only real acid around when you put a strong acid in water is going to be H3O+. And that doesn't matter, whatever the strong acid is, it's going to make H3O+. So all strong acids will thus only be H3O+ in aqueous solution, and thus have the same strength. You can have pure solutions of a strong acid, and then yes, you can compare different strengths of them, but typically we don't ever use those pure solutions. We use solutions that have been diluted into water. Okay, so the last definition we're going to talk about, acid-base definition in this class, is the Lewis acid-base definition. So just to remind ourselves, the first acid-base definition was the Arrhenius definition, and that classified an acid as something that raised the H3O+ concentration in water, and a base was something, an Arrhenius base was something that increased the OH- concentration in water. Okay. The Bronsted-Lowry definition was all about proton transfer. So an acid was something that had a proton and could transfer it, and a base was something that had a lone pair of electrons and could pick up a proton. Right? The Lewis acid-base definition now is a little bit different. It is based on electron donation. So not proton donating, but electron donating. So a Lewis base is something that donates an electron pair to form a bond, and a Lewis acid is something that accepts an electron pair to form a bond. So a Lewis base is an electron donor. A Lewis acid is an electron acceptor. So Bronsted-Lowry, where typically the donor is an acid, the acceptor is a base. This one's a little bit flipped because we're talking now about electrons instead of protons. In this definition, you form this acid-base reaction forming a covalent bond. So a Lewis base, if we think about what can be a Lewis base, it's very similar to a Bronsted-Lowry base in the fact that you have to have lone pair of electrons. Right? In Bronsted-Lowry, you needed to have that lone pair of electrons to accept a proton, but in Lewis definition, you have to have it to be able to donate them. Okay, so any substance that's a Bronsted-Lowry base is therefore also a Lewis base. The opposite of that is not true. Things can be Lewis bases that aren't Bronsted-Lowry bases because maybe they're not accepting a proton, they're forming a bond with some other element. Okay. A Lewis acid must have a vacant orbital. Okay, so that's something that it can use to accept a lone pair and form a new bond. Many substances that aren't Bronsted-Lowry acids are Lewis acids, okay, because it has nothing to do with protons. You only need to be able to accept electrons to form a bond. Okay, so therefore this Lewis definition expands what we could consider acids. Right, so what can be acids in this Lewis definition? Well, electron deficient molecules. Right, so things like boron and aluminum often form electron deficient molecules, right, that they don't have an octet. And because of that, they have unoccupied p orbitals that can accept pairs of electrons. So in this example, we have boron trifluoride, and it is going to be accepting this pair of electrons from our Lewis base, ammonia, and forms that adduct, that Lewis adduct, which is the combination of our Lewis acid and Lewis base, forming a covalent bond between the two. You can also have a case where a Lewis acid is a polar molecule with multiple bonds. So something like SO2 is going to be a polar molecule, has multiple bonds. So your base here, our base is actually water, and the electrons are being donated from the oxygen on water. You'll discuss this a lot more when you talk about organic chemistry when you get into that. But you have this electron pair attacking this sulfur, and it's an electrophile, meaning it wants more electrons because it has this partial positive charge. The oxygens are more electronegative, so they draw electron density away from that sulfur. It makes it positive. And so those electrons can actually, what we can call attacking when you show this arrow to it, and that helps form a bond. And when it does this, we have forming a bond here would actually make too many bonds on sulfur and change the formal charge. So what you get is one of these bonds in the double bond, those two electrons will move solely onto the oxygen, which then can grab the proton away from this water. Okay, very complex thing for this class. You'll see more of this in organic chemistry, this type of reaction mechanism, as they call it. But all you need to know in this class is that if you see this reaction written, this is the example of a Lewis acid, Lewis base reaction to form an adduct. Metal cations can also act as Lewis acids. And so we saw this example before of you have a metal cation that's coordinated by water molecules. Well, simply the act of being coordinated by water here is making this a Lewis acid by definition, because electrons on those oxygens in the water are going to be donated to our metal cation to form these bonds, the coordination between water and that metal. And also you see many examples of small metal cations in biology. So this is a magnesium cation that's in a chlorophyll, right? So this is our big chlorophyll molecule. Obviously, you're not going to have to draw this or know anything about it for this class. But if you go further on into like biology or biochemistry, you'll run into these in metal cations in the active site of enzymes, or in this case, like in a chlorophyll or a heme group in hemoglobin. And they're coordinated by nitrogen atoms in those ring structures. And those nitrogen atoms are donating electrons to the magnesium and coordinating it, bonding it in there. And so magnesium is acting like a Lewis acid. Okay, so let's try one last practice problem, trying to identify Lewis acids and Lewis bases in the following reactions. So H plus OH minus goes to H2O. So this is our sort of our definition, our Arrhenius definition of an acid-base neutralization. Okay, and you could kind of think of, in terms of Bronsted-Lowry as well, the H plus would be the acid. It's donating it to OH minus, which is the base. Okay. In the Lewis definition, the Lewis acid is going to be the species that is accepting electrons. So proton here is going to be our acid in the Lewis definition. It's going to accept those electrons, and then accepting the electrons from the Lewis base, which is OH minus. And then our adduct would be H2O. In the second reaction, we have Cl minus plus boron trichloride, and we form boron tetrachloride. Okay, so remember, boron is one of those examples of an electron deficient molecule. It can make electron deficient molecules. So, right, it has 3 chlorines around it, only 3 bonds, doesn't have a full octet. So it can actually accept electrons, in this case, right, from chlorine, and we form BCl4. So chlorine is donating the electrons, so it is acting like our base, and BCl3 is accepting those electrons, so it is acting like our acid in our Lewis definition. Okay, finally, we have our small cation, potassium, being coordinated by 6 water molecules. Remember, those water molecules are now going to be donating electrons to that positively charged metal, so they will be our base. And potassium is accepting those electrons, so it is our acid.